Hello, 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 hello. Okay, so am I audible? Okay, so okay, so very good morning to everyone. So students, in the last lecture we have started there are various method by which we can determine the mechanism. So in that we had learned the product analysis. So by analyzing the product we can determine the mechanism of reaction. Okay, so in the last lecture we had learned that the addition of HCl to propene, it gives two different types of product. Okay, that is 2-chloropropane and 1-chloropropane. So so addition of HCl to propene gives the formation of 2-chloropropane as a major product. Okay, and this clearly indicates that the mechanism involves Markovnikov's rule and the formation of more stable secondary carbocation. Okay, so by analyzing the product we can determine the mechanism. So you are getting 2-chloropropane as a major product. So you can say that this reaction what involves the Markovnikov's rule. Okay, addition of HCl to propene involves the Markovnikov's rule. Okay, on the basis of Markovnikov's rule, and in this reaction there is a formation of carbocation as an intermediate. Okay, and more stable secondary carbocation is formed during this reaction. Okay, so you know that between this primary and secondary your secondary carbocation is more stable as compared to primary, so that's why you are getting more percentage. Okay, you are getting major product as a 2-chloropropane. Okay, so again in the last lecture we had learned the hydrolysis of isomeric allylic chloride gives mixture of 85% tertiary alcohol and 15% primary alcohol. So in this reaction also isomeric allylic chlorides hydrolysis reaction. So hydrolysis of this allylic chloride takes place and you will get the intermediate, that is primary carbocation and tertiary carbocation. So there is a rearrangement of this carbocation takes place from primary to tertiary, because the tertiary carbocation is more stable carbocation than primary. So rearrangement of this carbocation takes place, and next step is what your water molecule attack on that carbocation, and you will get 85% tertiary alcohol and 15% primary alcohol, because in your reaction mixture more amount of your intermediate present in a tertiary carbocation, so that's why you are getting 85% tertiary alcohol, and 15% primary alcohol. Again in the last lecture we had learned what the product analysis of Beckmann rearrangement. So earlier it was believed that the oxime which yield the amide passes the migratory group nearer to R dash group, or nearer to leaving group. Okay, however later on it was found that the one of the oxime, that is 2-bromo-5-nitro-acetophenone readily undergoes ring closure reaction, while another isomer of this 2-bromo-5-nitro-acetophenone undergoes Beckmann rearrangement. Okay, so identification of product leads to conclusion. That the rearrangement involves transmigration of substituted phenyl group. Okay, again in the last lecture we had learned the product analysis of this Claisen rearrangement. Okay, so this Claisen rearrangement, it is nothing but the rearrangement of allyl phenyl ether. Allyl phenyl ether is converted by heating into orthoallyl phenol. Okay, so so we have taken the example, that is one of the allyl phenyl ether. Okay, that is not substituted. Okay, so in that first reaction you will not get the mechanistic information. So in that what identification of does the product does not provide the mechanistic information. So in that reaction, the carbon atom breaks away from the linkage, and the same carbon atom that's become attached to the ring. So in that reaction, what we are not getting the mechanistic information, okay. But when we are doing the same reaction with the substituted allyl phenyl ether, okay, the formation of product gives the what in that formation of product allyl phenol, it tells us that during the rearrangement your gamma carbon is attached rather than alpha, okay. So this identification of product, okay, will get the correct information. So during the rearrangement your gamma carbon is attached to the ring carbon rather than alpha one. So this is just a revision that what we had learned in the last lecture. So student, today I am going to teach you uh, I'm going to teach you we can determine the mechanism by studying by kinetic studies, okay, by kinetic study. So by kinetic study you can also determine the studies, kinetic studies. So by your what you are doing the kinetic experiment, okay, okay. So and then you are what determining the order of that reaction, whether that reaction is first order or second order, okay. So and you will get the information about the order of the reaction, and what which type of intermediate or a transient state formed during that reaction, okay. So from that you can determine the mechanism of reaction, okay. So the kinetic studies gives lot of information, kinetic study gives lot of information which may give possible pathways of reaction, which may give possible pathways of reaction. The rate of reaction is the rate at which reactant disappear. Rate of reaction is nothing but the rate at which reactant disappear or product appear at particular time, at particular time. The rate of reaction is found by change in a concentration, color, conductivity, or any other properties that varies with the time, okay. So the rate of reaction is found by change in a concentration, color, conductivity, or any other properties that change with the time, okay. So to understand these kinetic studies, okay, let's take an example of SN2 reaction. So let's take example of SN2 reaction. So SN2 reaction is nothing but what your methyl bromide react with your hydroxide ion, okay, and you will get a methyl alcohol as a product. So in alkaline hydrolysis of primary alkyl halide, so your methyl bromide is a primary alkyl halide, okay, halide. The rate of reaction, so in this rate of reaction it depend on the concentration of both alkyl halide and nucleophile, alkyl halide and nucleophile. So let me show you that reaction, okay. SN1, it react with your methyl bromide, okay, and you will get methyl alcohol as a product, plus hydrogen, hydrogen. Here is the incoming nucleophile, SN2 reaction, transition state in SN2 reaction. Transition state in SN2 reaction, okay. So this is your primary alkyl halide, okay, nucleophile, it attack on backside, okay, it attack from backside, and when it attack from backside this CBr is a leaving group. So it so here this SN two reaction. It involves the inversion of configuration. Suppose your product is R, so you are getting S. So the reason is what? Your nucleophile attack from backside and it replaces the leaving group. Okay, so in this reaction the transition state, so this is your transition state involves both your nucleophile as well as alkyl halide. So the rate of reaction depends on both alkyl halide as well as nucleophile. So and the reaction is second order. So what in this, what you are doing the experiment. Okay, you are doing the experiment, then you are doing the kinetic studies of this experiment, then you will by calculation, okay, you can easily find out the order of reaction, and by finding out the order of reaction you can say that the given reaction, it is a second order reaction, and the transition state involves both your nucleophile as well as alkyl halide, and the rate of reaction depends on both your alkyl halide and nucleophile. So rate is equal to K CH3 OH CH3Br OH. So rate of reaction depends on both your nucleophile and alkyl halide. Nucleophile and alkyl halide. Okay, so the alkaline hydrolysis of primary alkyl halide, the rate of reaction depends on concentration of both alkyl halide and nucleophile, and this information suggests that the transition state involves both the alkyl halide and nucleophile, which then changes into product. Now let's take another example, kinetic studies, that is alkaline hydrolysis of tertiary alkyl halide. So in that reaction, in rate of hydrolysis of tertiary alkyl halide, the rate of reaction depends only on the concentration of alkyl halide. The rate of reaction in tertiary alkyl, the rate of reaction depends only on concentration of tertiary alkyl halide, and it is independent on concentration of nucleophile. Okay, thus both the alkyl halide and nucleophile are not involved in this step, in the same step, and so you can say that this reaction must be a two-step reaction. While in this first one, in the rate determining step, both your transition state and alkyl halide are involved, so you can say that this reaction is a one-step reaction. While in a alkaline hydrolysis of tertiary alkyl halide, the rate of reaction depends only on alkyl halide, not it is independent on concentration of nucleophile. Okay, so so thus both alkyl halide and nucleophile are not involved in the same step. So you can say that this the alkaline hydrolysis of tertiary alkyl halide, it involves two step, or it's a two-step reaction. So let me show the reaction tertiary alkyl halide. CH3 your Br, tertiary alkyl halide. ठीक है, it react with your oxide. Then reaction arrow. This alkyl halide convert to alcohol. Alkyl halide convert to alcohol. First reaction only on rate is K, depends only on alkyl halide, concentration of alkyl halide. So rate is equal to CH3 CH3 Br, CH3C Br. CH3C Br. CH3C Br. So the alkaline hydrolysis of this tertiary butyl bromide, okay, the rate of reaction depends only on the concentration of this your tertiary butyl bromide, not on the concentration of your nucleophile. Okay, it is independent on the concentration of your nucleophile. Okay, thus you can say that in the rate determining step only one molecule is involved. Okay, and you can say that both the alkyl halides and nucleophile are not involved in the same step. Okay, and thus you can say that this reaction must be a two-step reaction. This reaction must be a two-step reaction. Okay, so we'll see its mechanism. Step 1. Okay, so the say step 1, the ionization or the breaking of CBr bond takes place. Breaking of CBr bond takes place. Okay, so first step is a slow step. First step is a slow step. Transition state first. And this carbocation intermediates, these are electron deficient species, and you will get your Br minus. You will get your Br minus. You will get your Br minus. Now this is your first step, breaking of CBr bond, and this is a slow step. Okay, CBr bond breaks heterolytically. Okay, it will give you the formation of carbocation and this Br minus. Now steps 2. The first step. Okay, and So when this OH minus attack on this carbocation, that is your transition state 2, that is your transition state 2. Third point, detection and trapping of reaction, Remer-Timmer reaction. So this Remer-Timmer reaction okay, so in the Remer-Timmer reaction, the your aromatic alcohol your activated alcohol your what the compound that having activating group, okay, aromatic compound that having activating group like OH, NH2, okay, when the such compounds are reacted with the chloroform, such compounds are reacted with the chloroform in presence of KOH, in presence of KOH, you will get aromatic aldehyde as a product. That reaction is called as Remer-Timmer reaction. Okay, so in this reaction we are about reacting your activated aromatic compound that having activated group. So let's take an example. Let's take an example of Remer-Timmer reaction. So this is your, what is the name of this compound? 3CHCl Cl3 plus, okay, this reaction is called as a Remer-Timmer reaction. So so what we are doing this reaction, okay, and we are going to find out which intermediates are formed during this reaction. Okay, so the first step of this reaction, this is the pure reaction, okay, Remer-Timmer reaction. Your alcohol react with Cl3 in presence of KOH, okay, so you will get this aldehyde, aromatic aldehyde as a product. Okay, so this is the reaction that used for the formation or used to produce aromatic aldehyde. Okay, so in this reaction CH, this is your chloroform, okay, KOH, it react with potassium hydroxide, and okay, when it react with potassium hydroxide, you will get the intermediate CCl2 plus 2 second reaction second. Okay, so this is your alkene CH2CH2 so it's a CHCl2 ClH2 C hydrogen Cl Cl carbene as a product, ठीक है. So your reaction mechanism is very simple. Your KOH react with this chloroform, it takes proton, generate carbene. Okay, so here C bare bond is there, one electron shared by carbon and one electron shared by this your hydrogen. Okay, so this KOH takes this hydrogen as a H plus and both the electron remain on this carbon, so that's why there is a negative charge. Okay, then this Cl group leave as a Cl minus and it generate this carbene as a intermediate, generate carbene as a intermediate, and you will get this KCl, K and one Cl, they form KCl and H2O. Okay, this OH minus take this proton, convert to H2O. This K react with this Cl, form KCl, so you will get this carbene as intermediate, KCl, potassium chloride and water mole. Now this is the intermediate that is formed during the reaction. Okay, the next step, what you are reacting this ethene with CCl2. Okay, CCl2, the formation of cyclopropyl ring. It is a concerted type of reaction. Okay, so carbene, it is electron deficient species. Double bond will attack on this this your carbene. Okay, so on this carbon there is generation of carbon positive charge. So same, then this carbon will attack, or this electron will form this carbon will form bond with this carbon. So it is a concerted type of reaction. Okay, and we get this product. We will get this cyclopropyl chloride as a product. So by analyzing by detecting and by trapping and detecting the intermediate, you can determine the mechanism of reaction. So in this reaction, Remer-Demer reaction, the carbene is generated as the intermediate. So you can say that in this reaction, carbene has generated the intermediate. Okay, so it's electron deficient species. So first this reaction will take place. CaCl3 react with your chloroform. Okay, chloroform react with KOH, it will generate carbene as the intermediate. Okay, then this we are trapping this carbene. By using this ethene. Okay, so carbene immediately react. It's a short-lived species. एकदम कमी म्हणजे जास्त वेळ टिकू शकत नाही तर intermediate. ठीक आहे, so what in the same reaction we are adding some amount of your ethene. Okay, so that carbene immediately react with your ethene and it will form cyclic product. Okay, and some amount will react with the your phenol and it will form the formylation of phenol. Okay, so by analyzing the product, first you have trap this intermediate into this cyclopropyl ring. First what you have trap this intermediate and we have into this cyclopropyl ring, then you are detecting this product. Okay, and from that you can say that this reaction involves the formation of carbene as the intermediate. So hence you can easily tells that this reaction involves the formation of carbene as the intermediate, and you can easily determine its mechanism by detecting and trapping the intermediate. You can easily determine its mechanism by trapping the intermediate. ठीक है, so any doubt regarding this? Yes, hello, no, समझ लगा. ठीक है, So an intermediate is generally trapped by running the reaction mixture in presence of compound with which it reacts. Okay, so we are in trapping. What we are doing is that an intermediate is generally trapped by running the reaction in presence of compound with which it reacts. Okay, so this is your intermediate, and we are running the reaction with the compound with this intermediate is react. So this reactive compound is your ethene, so we can carbon can easily react with this ethene, and you will get this product. Okay, so in this way we can trap this intermediate. Okay, and compound and intermediate is generally trapped by running the reaction in presence of compound with which it reacts. Okay, so another example is this about Remer reaction. Okay, and H mu you will get. Okay, so this your carbanion generated from this CH3. Okay, CH3N3, CH3N2. Okay, there is a positive charge on this nitrogen, CH2N2. Okay, then we are in presence of H mu. Okay, we are irradiating this carbanion in presence of H mu light. Okay, so breaking of this bond takes place. Okay, N2 group N2 molecule will leave, and you will get carbene as an intermediate, CH2. Carbene as an intermediate, CH2. Then we are, once you get this intermediate, okay, once this intermediate is formed, carbene. Okay, you know that the characteristic reaction of this carbene is that it react with your compound that having double bond. Okay, and it form cyclopropylene. So this is cyclohexene, it having this double bond. So this CH2 will react with this carbene, will react with this cyclohexene, and you will get the product is like this. Okay, you will get this type of product. Okay, so in this reaction you can say that this reaction involves the formation of carbene as an intermediate. Okay, and you are trapping that intermediate by reacting with this cyclohexene, and once you trap this intermediate, you are detecting that product. Okay, there are different techniques are there. Okay, and once you detect that product, this product has been formed, and you can say that this reaction involves the formation of carbene as an intermediate. Okay, so you can easily determine the mechanism of this reaction. And another example is the detection and trapping of intermediate, that will see the another intermediate. Okay, that is benzine intermediate. So benzine immediately react with anthracene, yield tryptophan. So this is your compound. Okay, N2 plus N2 plus. So in presence of H mu, light, CO2 N2. Okay, so loss of this CO2 and N2, you will get the benzene as the intermediate. You will get benzene as the intermediate. So you will get this benzene as an intermediate. You will get this molecule is called as benzene. This in as a product. Okay, so in this reaction also you can say that this reaction involves a benzene as the intermediate, and you are trapping that benzene intermediate because this benzene react easily with anthracene, and you will get this product. And by analyzing this product, you can say that this reaction also involves the benzene as a intermediate. Benzene as a intermediate. Let's take another example. NaNH2. So this NaNH2 is a strong base. It's a strong base hydrogen. So CH2 can react with Br2, can react with Br2. So addition of this Br2 with ethene. Okay, so it's the addition reaction, and in this addition reaction the carbocation is one of the intermediate that is formed during this reaction. Okay, so there is a double bond. Okay, attack on this Br. This Br is actually it's a polar. There is a slightly positive charge on one Br, and there is slightly negative charge on another Br. So double bond will attack on one Br, and formation of C-Br bond takes place, and one carbon loses its electron. So there is a positive charge on that carbon. Now another Br adds to that carbocation, and you will get 1,2-dibromo as a product. 1,2-dibromoethane as a product. 1,2-dibromoethane as a product. PR. Okay, so this is the intermediate. Okay, formed during this reaction. So nucleophiles, so to detect this intermediate, to detect the carbocation, nucleophiles are used to trap the carbocation. Nucleophiles are used to trap the carbocations. The direct evidence that the addition of halogen to alkene proceeds through the formation of intermediate carbocation, and it is obtained by perform the reaction in presence of other nucleophile. In presence of other nucleophile, when the mixture of products are formed, and when the mixture of product will be obtained. Okay, and from that you can say that the given reaction involves the carbocation as intermediates. That's why we are getting the mixture of product. That's why we are getting mixture of product. So we are reacting this intermediate with we are doing this reaction with a mixture of nucleophile. The mixture of nucleophile. So the nucleophiles are OH minus, then I minus, Cl minus, ठीक है. Iodide, OH minus, nitrogen, CH3, 3. CH3, AIBN, azobis isobutyl nitrile, azobis isobutyl nitrile. Okay, so heating this molecule, the homolysis of this molecule takes place. Okay, it generates N2 molecule and 2 CH3 C N radical. So here is your, it's not a CH3, it's a CN N. So we are hitting this molecule. Okay, and the homolysis of this molecule takes place. So here we are using single headed arrow for homolysis. This bond will break homolytically, generate C radical. Same way this bond will break. Okay, same way this bond undergoes, this CH3 N bond undergoes homolysis. It generates N2 N2N CH3 CN. plus N2. Okay, so you will get this radical. Okay, now we are trapping this radical, we are reacting this radical with nitric oxide. Nitric oxide O, ठीक है. So it will react with nitric oxide and we will get the product. Oh.